In this video, we are going to compute the Laplace transforms of cosine of omega t and sine of omega t, where omega here is just a real number affecting the periodicity of those functions. We will then solve a first-order differential equation using the Laplace transform. All right, we can get both of these Laplace transforms at the same time if we use Euler's formula. So recall that e to the, I'm going to write down I omega t. So this complex exponential can be written in terms of cosine and sine as cosine of omega t plus I sine of omega t. Let's take the Laplace transform of both sides. So just transform the left-hand side and transform the right-hand side. I'm going to go ahead and break that apart using linearity. So when I take the Laplace transform of cosine plus I sine, that is the Laplace transform of cosine of omega t plus I times the Laplace transform of sine of omega t. All right. Let's look at the left-hand side. This is the Laplace transform of an exponential function, and we have already seen what that looks like. So we had from the first lesson that the Laplace transform of e to the at was 1 over s minus a, where here s was greater than a. When we computed the improper integral that gave us this Laplace transform, it did not depend on a being real. So we anti-differentiated with respect to t. A is just a number. It could be real or complex. So that means that I can do the Laplace transform now of this complex exponential using this formula. All right, it's going to be 1 over s minus I times omega. So I omega is like a. This is a complex number, but it's not how we like to write complex numbers. We would like to see real component plus I times the imaginary component. To convert this to that form, we need to take the denominator and multiply this expression by its complex conjugate. So divided by itself so that we're not actually changing anything. So we will multiply this by s plus I omega divided by s plus I omega. All right, when we do that, the numerator is just going to be s plus I omega. For the denominator, we multiply these two expressions together. We'll have s squared plus I s omega minus I s omega, so those middle terms cancel out, and then minus I squared omega squared. But I squared is -1, so minus I squared omega squared is really just plus omega squared. So the product of these two expressions in the denominators is going to be s squared plus omega squared. Let me now take this numerator and break that into two separate expressions where we have s divided by s squared. I'm having really bad luck with my markers. Sorry, just seem extra squeaky today. So s divided by s squared plus omega squared. Okay, there we go. Plus I times omega divided by s squared plus omega squared. All right. Compare this expression with this one. Cosine of omega t and sine of omega t are both real functions. We expect these to be real. So what we have here is a real component plus I times an imaginary component. That's going to pair up directly with this real component and this imaginary component. So we match like terms here, where like means real with real and imaginary with imaginary. So we're done. We've got both of these Laplace transforms at the same time. In particular, we can say that the Laplace transform of cosine of omega t is equal to this real term, s divided by s squared plus omega squared. And similarly, the Laplace transform of sine of omega t is equal to this component here. So the Laplace transform of sine of omega t is equal to omega divided by s squared plus omega squared. Like that. The domain for s here is s greater than 0. It's not immediately apparent from anything I've written up here why it's s greater than 0. But if you revisit the improper integral that we evaluated when we came up with this expression, s greater than a, we were treating a like a real number. But if you replace it with a complex number, what you would find is actually the bound should be s greater than the real part of a. That's what you would need in order to make that improper integral converge. So here, for our complex exponential that we evaluated to get to these expressions, these were complex. They were pure imaginary, which meant their real part was 0. So the bound is s greater than the real part of this pure imaginary number, so it's s greater than 0. Now we're going to use the Laplace transform together with some of these facts that we've collected about it in order to solve this differential equation. We would like to find the function y of t satisfying dy dt equals 4 times y minus cosine of t with an initial condition that when t equals 0, y equals 0. What we're going to do is take the Laplace transform of both sides. So on the left, we have the Laplace transform of dy dt, and on the right, the Laplace transform of 4y minus cosine of t. What I would like for you to do now is pause and take this as far as you can. Here are the steps that I hope you went through. Using this first identity for the derivative of a function, or rather its Laplace transform, we can rewrite this left-hand side as s times the Laplace transform of the unknown function y minus y evaluated at 0, which we know to be 0. On the right, we can break that apart using linearity. The 4 comes out. We have 4 times the Laplace transform of y minus the Laplace transform of cosine of, let me write 1t, just to emphasize here that omega is 1. Okay, another remark is that y of 0 is 0, so that's nice. We would like to solve for Laplace transform of y like a variable in an equation. So I would like to isolate this expression. Let me move this one on the right over to the left. We'll have s times the Laplace transform of y minus 4 times the Laplace transform of y, which we can write as s minus 4 times the Laplace transform of y. If our initial condition was not 0, we could move that to the right, but we don't have to worry about that in this particular example. What is negative 1 times the Laplace transform of cosine of 1t? We know that's negative s divided by s squared plus 1 squared. I'll write that, 1 squared. Okay, I'm just going to write 1 squared once, just to emphasize that 1 is omega. Now we can isolate Laplace transform of y. We have negative s divided by s squared plus 1 in the denominator times s minus 4. This needs partial fraction decomposition, and in particular, we're going to look for 2 expressions. The first one will have a denominator that's s squared plus 1. This is an irreducible quadratic, so we don't have to factor that. It's just s squared plus 1. And the second one is s minus 4. So it's not too bad of a partial fraction decomposition. They're just 2 terms. Because this is quadratic, the appropriate unknown numerator should take the form as plus b, and this one is just going to be c. All right. All right, you may have already done this, but if you haven't, go ahead and pause and see if you can work out the unknown numbers a, b, and c. All right, what you should have found from the partial fraction decomposition is that this coefficient a here is 4 over 17, b is negative 1 over 17, and c is 4 over 17. Sorry, negative 4 over 17. I'm going to rewrite this down here and then erase this so that you can see me again. But before I do that, I wanted to also break up this numerator, and I want to talk you through it too, because this is the first time we're looking at this kind of expression. A, or 4 over 17, is a number, and then I have s in this first expression divided by s squared plus 1. That looks a lot like this s here. So this piece, s over s squared plus 1, that looks like maybe it was the Laplace transform of cosine of 1t. On the other hand, a constant over s squared plus 1, well, if I pull the constant in front, I would be looking at 1 over s squared plus 1, which again looks like a Laplace transform of a trig function. This time it's sine of omega t. Okay, so let me rewrite this. as 4 over 17 times s over s squared plus 1. That's what we are going to identify as the Laplace transform of cosine of 1t. Then minus 1 over 17 times 1 over s squared plus 1, where here 1 is the appropriate value for omega. And then minus 4 over 17 times 1 over s minus 4, where s minus 4, just like our familiar exponential transform. Okay, I'm going to step aside for a second, then when I come back, I'll have erased this, and we will finish this computation. Let's finish this computation by putting this entire right-hand side inside of a single Laplace transform using linearity. So this entire right-hand side looks like the Laplace transform of 4 over 17 times cosine of 1t. So 4 over 17 cosine of t minus 1 over 17 sine of t minus 4 over 17 e to the 4t. We can invert the Laplace transform now to say that since y and this expression have the same Laplace transform, y is this expression. So y is this. I don't want to rewrite this whole thing one more time. So let me just underline this and say that this function, 4 over 17 times cosine of t minus 1 over 17 times sine of t minus 4 over 17 e to the 4t, this is our solution y of t.